Two strangers are racing toward the same star, and the calendar says their sprints finish almost together. One comes from deep interstellar night, unbound and fast. The other rises from our own distant backyard, bright and brazen. Their closest approaches line up within a few weeks. Our best telescopes will go blind at the climax. That should not happen so neatly, yet it is happening now. We have a mystery with a countdown. Join the investigation and help us track the finale. Like, subscribe, and stay with us for the reveal. Look up on an October night and imagine a cosmic intersection taking shape far beyond the clouds. An interstellar traveler named 3i Atlas slices across the plane of the planets on a hyperbolic path that will never loop back. A long-period comet named SWAN R2, likely born in the distant Oort cloud, flares with a sweeping tail as it turns outward from the sun. They did not start together. They do not move alike, yet their timetables rhyme, and that rhyme is why astronomers keep checking the math. Start with the basics. We can say plainly. 3i Atlas is retrograde, which means it swims upstream against the general spin of the solar system. Its orbit is not an ellipse that returns. It is the open curve of a one-time visit, the mathematical signature of a guest from another star system. SWAN R2 is a different kind of wanderer. It fell inward on a very long ellipse, woke under sunlight, and now wears the classic signs of a comet that is shedding gas and dust. Here is where the paradox sharpens. The significant milestones of both objects cluster inside a narrow window, measured in weeks. SWAN R2 reaches its closest approach to Earth in late October. 3i Atlas reaches closest approach to the Sun around the end of October and brushes the vicinity of Mars earlier that month. Independent origins, different dynamics, nearly overlapping finales. In a sky where rare events usually spread across years, this is tight choreography. You can feel the tug of that word choreography. Before we let it pull us into wild stories, we have to ask the sober questions. How often would a calendar cluster like this be expected across centuries of skywatching? How many visitors have we historically missed because they hid in sunlight or hugged the horizon? How much of the surprise is created by the geometry of observation rather than the physics of the visitors? Rare is not the same as impossible. Rare plus improved surveys can feel like fate when it is only statistics catching up. Now layer in the cruel timing that turns intrigue into urgency. As both objects near their most extreme heating, the apparent angle between them and the sun shrinks. Solar glare overwhelms ground-based optics. Coronagraphs help, but they are not magic windows. For a spell, the instruments that talk to us the most will fall quiet. The moment most likely to transform these objects will unfold while we face a bright curtain and listen for anything that leaks around the edges. That temporary blackout sets the stakes for everything we do before it. We bank spectra and images now so we can compare after the glare. We watch brightness curves for subtle kinks that might signal new jets starting or surfaces turning. Map tail structure and color hints. We enlist every asset with a slightly different angle, including spacecraft around Mars that can look from a position off our line to the sun. When the lights come back, even modest changes will speak loudly because we will have a locked baseline. Part of the allure here is visual. 3i Atlas often shows a cool green tint, with the kind of color that makes photographers cheer and skeptics ask careful questions. Green can arise from diatomic carbon and from cyanogen, molecules that light up under ultraviolet sunlight. Beautiful does not automatically mean extraordinary. It means the chemistry is active and the coma is doing what coma do, turning sunlight into a fingerprint we can read. Beauty can be a clue, not a verdict. Part of the allure is numerical. The phrase, once in millions of years, flows easily in headlines, yet probability over cosmic time is slippery. In a galaxy-scaled lottery with uncounted tickets, rare pairings eventually happen. Our job is to weigh wonder against mechanism. Do the orbits and the timing fall inside the broad bell curve of nature? If yes, we celebrate the luck of being here to watch. If no, we raise an eyebrow and tighten tests that could break a simple explanation. There is also the human rhythm of a season to respect. October is a month of long twilights and falling temperatures in many places. It is also a month of sky stories. That makes a perfect stage for a double act with a hidden finale. We will keep the pace brisk, balancing narrative beats with quick explainers. We will share the rules that would reveal real engineering if it were present, and the signatures that would confirm natural physics if that is all we are seeing. Either way, we learn something true. So this is our plan as the clock ticks. We keep the paradox in view without letting it run the show. We savor the spectacle and ask for receipts. We prepare for silence by writing down what the sky says now, while it is still speaking. Then we wait together for the curtain to lift. When it does, the data will either kiss the models or slap them. Both outcomes are good for science. Both outcomes are good for curiosity. We will be here to translate whichever shows up first. Start with the interstellar one. 3I Atlas was first noticed as a faint, out-of-place pixel by the Asteroid Terrestrial Impact Last Alert System in Chile on the 1st of July, 2025. Within hours, the orbital math said what the sky had been whispering. This traveller is unbound to the sun. The path is hyperbolic. The inclination is near 175 degrees, which means it swims almost headfirst against the traffic of the planets. That is, the signature of a guest from somewhere else, a system not our own, a shard of somebody else's formation story finally drifting through our neighbourhood. Seen through small telescopes, 3I Atlas often wears a cool green haze. That colour is a clue more than a headline. Sunlight knocks energy into simple carbon molecules that fluoresce in green, and cyanogen can help if the coma is rich and active. Beauty does not automatically equal artificial. It does mean the chemistry is awake and readable. Spectrographs add more texture. Powerful instruments reported strong nickel emission lines, without the iron signals that usually tag along in familiar ratios. Strange? Yes. Impossible? No. Space weathering, unusual bonding partners, and layered ices can skew what glows first as sunlight ramps up. Zoom out from the chemistry to the shape and pacing. Hubble-class images and careful modelling suggest a nucleus only a few kilometres across, modest by Comet standards, compact and purposeful in its appearance. James Webb Space Telescope observations at large distance lean toward carbon dioxide, driving early activity while water stayed quiet in the cold. That is a pattern seen before in distant comets that wake early, and it fits the picture of a visitor with volatile ices ready to sublimate long before the classic snow turns to gas. The track will bring 3I Atlas near Mars in early October, at a respectful tens of millions of kilometers. Closest approach to the Sun lands around the end of October, still outside Earth's orbit and safely distant from us. This is a show, not a threat. Now meet the homegrown spectacle. SWAN R2 comes from the long quiet between the stars and the planets, a reservoir called the Oort cloud that holds the deep freeze of our own system's youth. It was flagged in early September by an amateur scanning images from the Solar and Heliospheric Observatory, the instrument called Solar Wind. Anisotropies maps hydrogen, which makes it surprisingly good at catching comets that are otherwise hiding in solar glare. One day, the maps looked ordinary. Then a smudge brightened and refused to behave like background. A binocular comet had stepped into the light. SWAN R2 is everything people hope comets will be. A head bright enough for casual observers in dark skies, a tail that can stretch for degrees of sky, shaped by sunlight and wind, from the sun into a sweeping brushstroke. The orbit is the long-drawn ellipse of a classic long-period comet. It dove inward, looped within about half an astronomical unit of the sun in mid-September, then started the long climb outward. The geometry for Earth keeps improving through October, which is why photographs began to leap off screens, and why you may hear someone in your life say they saw a ghostly fan leaning up from the western twilight. Because this is a science story, we keep the numbers honest. Closest approach to Earth comes in late October at about 1/4 of an eye. Astronomical unit, roughly tens of millions of kilometers. That is close in conversational terms and very far in safety terms. The brightness will dance because comets are messy. Different ices wake at different distances. Rotation moves active regions in, and, out of sunlight, dust jets can surge and fade. All of that adds drama without adding danger. The pairing works because the contrasts are sharp. 3I Atlas is small, green-tinged, and on a once-only path that cuts across the plane of the planets in retrograde. SWAN R2 is sprawling, dust-rich, and on a path that belongs to us. A child of the same protoplanetary disk that made Earth long ago. One is a needle of light that suggests speed and intent. The other is a veil that turns a wide patch of sky into a living painting. Different births, different behaviors, different futures. And yet the calendars rhyme SWAN R 2 peaks for the public in September and October, then glides past Earth's best angle around the 3rd week. Of October, 3i Atlas tips into closest approach to Mars at the start of the month and slides toward its own solar minimum distance. As October ends, the eyes of Earth begin to fail precisely when the thermodynamics get interesting. That is the knot at the heart of our story. 2 travelers who should not share a stage end up with curtain calls that almost touch, right when our view narrows to a slit. Before we leap to meaning, we keep our footing on what is solid. Discovery dates are pinned by survey logs. The interstellar identity is written in the open curve of the hyperbola. The long period status is written in the stretched ellipse that returns only after spans. Longer than civilizations, the colors are chemistry we can simulate on a bench. The distances are friendly. Everything extraordinary so far can live inside natural explanations. Still, you can feel the pull of the question. Is this just the universe, rolling a rare alignment in front of a species that finally has enough cameras to notice? Or is there something deeper humming under the data, a pattern we have not named yet? The only way to answer is to keep the profiles straight, keep the baselines clean, and keep the tests ready for the moment. The glare lifts. Meet the visitors. Remember their differences. Hold the timing in your mind. The next steps will either make that timing look ordinary, or they will make it the opening line of a new chapter. Picture a planet wrapped in quiet telescopes that do not blink. Every clear night they sweep the sky. Take a picture, wait a breath, take another, and ask a simple question. What changed? That is how a faint-off pixel becomes a story. The asteroid terrestrial impact last alert system in Chile did exactly that on the first night of July. A point drifted against the star field faster than the background allows. The pipeline flagged it. Humans leaned in. Within hours, the math said, hyperbola, retrograde, unbound. The spark had become a signal. Difference imaging makes this possible. Subtract last night from tonight, and the steady stars cancel out like a solved equation. What stays behind are the movers and the variables. Asteroids crawl, satellites streak, noise flickers, and dies. A. Candidate remains if it moves with the sky, not with the hardware. The software measures the position with exquisite precision, tags the brightness, and builds a small stack of observations across minutes that becomes the seed of an orbit. The seed goes to a central clearinghouse and waits for friends. If the same point shows up again from another telescope with the right geometry, the orbit sprouts leaves. The Catalina Sky Survey and other ground networks add coverage from different longitudes and latitudes. When one night ends in Arizona, another begins in Chile, then in the Canary Islands, then in Hawaii. The Skynet never sleeps, because the planet keeps handing the night around. This relay lets small motion turn into trajectory, not just a direction, but a living path in 3 dimensions that can be run forward and backward to test what makes sense. That is how once-only visitors reveal themselves. They do not close the loop. Above the atmosphere, another detective watches in a different way. The Near-Earth Object Wide Field Infrared Survey Explorer measures thermal glow rather than reflected starlight, which is especially helpful for dark objects that swallow visible light but still radiate heat. What is cold to us can be bright to an infrared eye. Combine this with ground images, and you get size hints, not just brightness. A small, shiny object can mimic a big soot, dark one in visible light. In infrared, the disguise slips. Closer to the sun, there is a specialized instrument that loves water. The Solar and Heliospheric Observatory carries solar wind, anisotropies, a device that maps hydrogen from broken water molecules. Fresh comets leak water and the fragments light up. Even when a comet hides in glare, the hydrogen can betray its presence. An amateur scanning those maps saw SWAN R2 as a stubborn brightening that would not fade with instrumental noise. That is the human in the loop. The code whispers, maybe a person says, take a second look. Not every blip becomes a headline. The pipelines are designed to kill false positives all day. Hot pixels masquerade as motion. Airplanes paint faint streaks. Cosmic rays smack the detector and pretend to be a star for a heartbeat. Algorithms learn habits and throw these out. Only patterns that repeat in the right way, across multiple frames, and often across multiple observatories, survive to the human team. Then comes astrometry, that pins sky, coordinates to catalogue. Stars, photometry that tracks light, and the first orbital fit that asks which family this traveler belongs to. Hidden inside that fit is geometry that shapes what we can see. The angle between a target and the sun matters more than anyone wants to admit. If an object hugs the sun from our line of sight, the best telescopes on Earth are effectively blind during twilight and daylight. The Holacek effect explains why comets sometimes look like they appear from nowhere at low angles right after sunset. They were there for weeks. Only the glare kept them invisible. This is not mystery. It is perspective. The net is global, yet imperfect. Long tails of data pour in nightly, measured in hundreds of gigabytes, then in terabytes across weeks. The software must choose what to ignore so it can finish before dawn. That means thresholds. Thresholds mean trade-offs. Set them high and you miss faint things. Set them low and you drown in junk. This is why amateurs become essential. A single person staring at a curious smear can trigger a follow-up that the threshold would have skipped. The best discoveries live at the edge of what is just barely there. Once a candidate graduates, the Minor Planet Center gathers reports, links tracklets that belong to the same body, and publishes provisional designations that start the clock for the community. Now the prediction engine spins up. Where should we point tomorrow to catch the same traveler again? The better the next measurement, the better the orbit, the better the prediction for the one after that. It is a feedback loop that turns a rumor into a trajectory you can plan around. Spectroscopy arrives as soon as the point is bright enough. A spectrograph spreads the light into a rainbow and carves it into lines that mean molecules and atoms. Diatomic carbon makes a green band. Cyanogen adds its own signature. Nickel can shout while iron whispers or stays silent. These are not decorations. They are thermometers and pressure gauges and chemical notebooks all rolled into one. The pattern on the sensor is the same pattern in the physics of the coma and the tail. The system also carries a warning we need to keep in mind. Algorithms are good at finding what they were trained to find. They love ellipses and slow drifts that fit expectations. Anything that misbehaves at the margins can be squeezed toward the nearest familiar shape by the filters that keep the flood manageable. That is why every step includes a human pause where a scientist asks whether the tidy answer actually fits the raw frames. The habit of doubt is not a mood, it is an instrument. So, when we say the Skynet found 2 visitors at once, we are really saying a community did. Silicon stared without getting bored. People noticed when an anomaly stayed put night after night. Ground telescopes passed a baton between continents. Space telescopes filled gaps where air would have blurred the story. Amateurs nudged professionals at the right moment. That is the machine that makes discovery feel inevitable in hindsight. It is also the reason we can tell the difference between a spectacular coincidence and a genuine Reuven pattern. The net does not only catch, it measures, checks, and argues with itself until the picture holds. Imagine the system as a tilted clockwork, with most planets skating along the same thin rink called the ecliptic. Now, picture 3i Atlas as the skater who dives in from underneath the rink going the wrong way, and never looping back. A hyperbola is an open road. Once it passes the sun, it is gone for good. Its tilt is about 175 degrees, almost a full flip against planetary traffic. SWAN R2 is the classic long ellipse. It dives inward, swings around the sun, then heads back out for a very long time before returning. 2 very different tracks, 2 very different rules of motion. One shared stage in October. When people hear that their big moments cluster within weeks, the gut says impossible. The math says rare but not forbidden. 2 trains can cross the same town in the same afternoon, even if they started on different continents. The trick is geometry. If the lines of their paths and the speed along those lines set close approach points in the same season, the calendar will rhyme. Over centuries, that rhyme will happen once in a while. Over millions of years, it becomes inevitable that somewhere, sometime, a pair will line up for an audience that happens to be awake and watching. To feel that geometry, shrink the space to 3 simple angles. Angle 1 is the tilt of the orbit relative to the planetary plane. 3i Atlas is almost upside down, which means it slices through the busy plane at a steep cut. SWAN R2 is tilted but still feels like family. Angle 2 is the angle between the object and the sun, as seen from Earth, called elongation in observatories and called can I actually see it by everyone else. Angle 3 is phase angle. the sun to object to Earth angle, that helps decide how much of the dusty coma and tail light up toward us. These three angles spin together through the month and decide whether a visitor is obvious or hidden, dramatic or dull. There is also speed along the path. Interstellar guests tend to arrive fast. They light up earlier than expected because volatile ices flicker to life at long distances, yet they still fly through the inner system in a rush. Long-period comets can loiter in slow arcs, then accelerate near the sun and surprise us as geometry improves. If the fast one and the slow one both have their visual sweet spots inside the same slice of the calendar, we get an overlap that feels like a plot twist written by the sky. Discovery bias pushes that twist further. Objects that approach along the glare of the sun remain off stage until the last moment. You hear this called the Holitschek effect, which is a fancy way of saying the sun ruins the view right when things get good. A comet can brighten for weeks, yet the improvement goes unnoticed because the angle is too small for safe observing. Then one evening, it steps out into twilight at just the right separation, and everyone decides it appeared out of nowhere. It did not. We finally had the angle. Gravitational mechanics add another layer of rhythm. Retrograde motion, like the path of 3i Atlas, changes how the sun and planets tug on a visitor. It moves against the flow, so the pattern of tiny kicks is different. Those kicks are not plot devices. They are small corrections that the orbit fit must respect. In practical terms, they do not spoil the show. They set the schedule that says Mars sees a pass in early. October, while Earth sits off to the side, then Earth loses both into glare as the month closes. The choreography is gravity plus perspective, not intent. If this all sounds abstract, try a street map version. Draw two long curves through a city. One is a highway exit that never circles back. One is a boulevard that loops through downtown, then returns to the suburbs. At some point, both pass within a few blocks of the main. Square. If you stand at the square during that window, you will swear the city planned a parade. If you move one block away at the wrong time, you might miss both and never know. Numbers steady the nerves. 3i Atlas aims for a closest solar distance around 1.35 astronomical units. Just inside the path of Mars, SWAN R2 met the Sun at about half an astronomical unit in mid-September, then arced outward while Earth slides into a better line of sight. Closest approach to Earth for SWAN R2 sits near a quarter of an astronomical unit later in October. None of this places either object on a collision course. All of it put them on a collision course with our curiosity. There is also a simple reason the window feels packed. We pay attention when the sky is kind to eyes and cameras. Early evening after the sun sets is when people look up. This is exactly when a comet leaving conjunction rises into view. It makes the month feel dense because our attention is dense. The daytimes when geometry is also changing do not count for most of us because we cannot see anything near the sun without special instruments. Human habits become part of the pattern we swear the universe is making. So the coincidence is a braid of 3 strands orbital paths that happen to swing near their milestones together, viewing angles that switch from impossible to perfect in a few nights, and human attention concentrated into the same hours across many viewers. Twist those strands and you get the feeling of fate. Untwist them and you get physics and perspective. The ore does not go away when you untwist it, it just grows. Cleaner, we can stand in October, admire the timing, and still credit the clockwork. Here is the payoff of understanding the geometry. It tells us where to place our bets for the next frames. As the elongation drops, Earth-based optics fade, so we lean on space observatories with coronagraphs and on Mars orbiters that sit to the side of our line. As phase angles change, tail structure can do sudden things like disconnect under solar wind stress or flare as jets rotate into sunlight. That is not magic. That is the dance of light and dust, playing out exactly as the angles demand. When someone asks how 2 strangers arrived on the same stage, we can answer without killing the wonder. They were always on their own paths. The stage is a slice of time when vantage makes both sing at once. Rarity is the spice, not the author. The script was written by gravity long ago. We just showed up for the right act. There is a moment in every close solar approach when the sky stops cooperating. As 3i Atlas drops toward the sun and SWAN R2 swings outward into brighter twilight, The angle between target and star shrinks. Telescopes love dark backgrounds and clean margins. The sun is the opposite of both glare floods. Optic sensors saturate. The scene we most want to watch slips behind a wall of light. Astronomers use a simple word for the key angle. Elongation is the separation between a target and the sun, as seen from your eye. Big elongation means easy. Small elongation means pain. Once an object slides too close to that blazing disk, the ground observatories lose contrast. Even high mountains cannot help much because the atmosphere scatters sunlight across the whole dome. Air itself becomes a bright screen between us and the faint thing we are trying to study. Coronagraphs sound like a cure, and in part they are. A coronagraph places an artificial little eclipse inside the instrument to block the sun, so faint structures around it can be seen. That trick gives us the solar wind and coronal streamers. And sometimes it gives us comets that dare to pass close to the sun. But every coronagraph has a blind radius called the inner working angle. Anything inside that tiny circle is invisible. Anything just outside is visible only if it is bright enough to stand above stray light and instrument noise. There is another challenge that feels more human than technical. The best ground telescopes operate at night. Twilight is a narrow window. If a comet spends most of its time only a few degrees from the sun, we get minutes at most to try a careful exposure before the sky brightens past the point of usefulness. Chasing a fading target in a brightening sky is like trying to read a candle label while someone turns up a floodlight. So we move the eyes. Spacecraft parked at the Sun and Earth. Lagrange Point 1 have a different view because there is no air to scatter light. Instruments like the hydrogen mapper on the Solar and Heliospheric Observatory can find a comet by tracking the glow of broken water molecules, even when the head is deep in glare. Solar imagers with coronagraphs can watch tails whip and sometimes snap under the solar wind. These assets cover part of the gap, yet they are built for the Sun first and comets second. Their cadence and sensitivity are not tuned to the subtle chemistry that fascinates us in interstellar visitors. The clever workaround is parallax on a planetary scale. When Earth lines up too close to the Sun-comet line, Mars may sit at a friendlier. Angle orbiters around Mars carry cameras and spectrometers designed for planetary science, but they can be pointed out to space during narrow windows. From that offset vantage, the coma can be measured and the ion tail geometry can be sketched while Earth is blinded. The result will not be glamorous postcards. It can still be priceless context that ties the before and after together. We also lean on timing. Before the blackout, we bank spectra. We measure brightness with care. We log tail position angles and look for faint disconnections where magnetic stress tore the ion stream. These are baselines. After the blackout, we will repeat the same measures and subtract. Change becomes the story. If the nickel lines fade or water lines surge, or the color tilts toward blue or red, we can map that shift to the heating that happened while we were blind. Engineers have another lever to pull that is less obvious than a new telescope. They can squeeze more from the instruments we already have. By rethinking exposure patterns and processing, short bursts can be stacked to beat the glare. Stray light models can be improved to remove ghosts that masquerade as tails. A tiny gain in dynamic range can turn a maybe into a yes when the target lives right on the threshold of detectability. The margin is thin, but science often wins by inches. There is also a discipline of knowing when not to look. Pointing a powerful instrument too near the sun risks damage. Teams set strict limits that protect mirrors and detectors. Those limits sometimes mean living with the blackout and planning the comeback as the main event. It may sound like surrender. In reality, it is strategy. A patient measurement after will tell us more truth than a reckless peek during. So this is the map through darkness. Accept the glare where physics demands it. Exploit every off-axis asset we can muster. Use Mars as a balcony seat. Turn pre-blackout observations into a crisp ledger. Then listen to the silence not as defeat, but as the setup for a clean test. When 3i Atlas and SWAN R2 step back into wider angles, we will compare line for line, curve for curve. If they behave like natural wanderers heated by a star, the ledger will balance. If they do anything wilder, it will show up as numbers that do not fit. Either way, the blackout ends with an answer. Stand under a dark sky, and you may notice that 3i Atlas wears a cool veil that leans toward green. Cameras make it pop. Eyeballs see it as a breath of color rather than neon paint. Still, the question bites. Why green? What is the comet telling us? And does that color hint at something engineered, or simply something waking up under sunlight? The short answer is chemistry. The longer answer is a beautiful little physics lesson that turns color into a story about molecules, energy, and time. Sunlight is more than light. It carries a flood of ultraviolet photons that punch energy into fragile molecules floating in a comet's coma. Some of those molecules respond by glowing at very specific colors, almost like musical notes, hit by an instrument that has only a few keys. Two usual suspects drive the green impression. One is a simple carbon pair called diatomic carbon. The other is cyanogen, a carbon and nitrogen combination that can glow in a way that nudges our eyes toward green when the emission blends across the camera sensor's filters. Think of diatomic carbon as a springy two-atom dumbbell. Ultraviolet sunlight excites its electrons to a higher energy state. When those electrons fall back down, the molecule spits out photons in a narrow family of greenish wavelengths. Cyanogen can contribute its own set of lines near the same neighborhood. The exact mix depends on how much of each parent molecule is freed from the ice and how hard the local sunlight is driving the reaction. Chemistry makes a palette. The sun chooses the brush pressure. There is a neat map inside a green comet that you can learn to read. Close to the nucleus, where fresh gas is dense and young, diatomic carbon has a chance to form and light up strongly. Farther out, sunlight tears that same molecule apart faster than it can be replaced. The result is a halo that looks more green toward the center and fades toward neutral in the outer coma. That gradient is not a mystery. It is a clock. It tells you how quickly molecules are being born and how quickly they die in open sunlight. Color alone never convicts or acquits. Camera settings matter. A longer exposure and a modern sensor can make a delicate tint look like a paint spill. White balance can nudge green one way or another. Processing can exaggerate or suppress hues. This is why professionals love spectra. A spectrograph spreads the light into a barcode where every line has a meaning. With that barcode, you can say, not just green, but which molecules, how strong, and how those strengths change with distance from the sun and with time. We should also clear away two common confusions that circle any green comet. First, green does not mean toxic in the way. A warning label means toxic. Cyanogen is indeed a nasty molecule on Earth in a closed room. In a comet's near vacuum, it exists at tiny densities that matter only for photons and physics. Second, green does not mean alien technology. Nature is very good at making simple molecules and making them sing under sunlight. The wonder lives in the elegance, not in the need for a hidden engine. That said, color can still act like a detective's hunch that leads to better questions. If the green stays unusually steady across a wide range of distances, that hints at a supply of carbon-rich parent molecules ready to keep feeding diatomic carbon as old gas breaks apart. If the green surges faster than the overall brightness, that suggests new active areas on the nucleus have rotated into sunlight and started venting fresh material. If the green tilts toward a different hue after perihelion, that can mean the balance of gases has changed, because deeper, less volatile ices finally woke up. 3i Atlas gives us one more twist. Some spectrographs reported metallic lines that also live in the green neighborhood. We will unpack those in the next part. For now, keep the principle simple. A single tint can arise from more than one source. Only high-resolution spectra tell you whether you are seeing mostly molecular bands from gas, narrow atomic lines from trace metals, or a blend. This is why teams rush to bank spectra early and often before the glare steals the view. Each snapshot becomes a rung on a ladder that we will climb again when the comet comes back into friendlier angles. Color is also a proxy for heat and distance. Diatomic carbon and cyanogen do not light up equally at all ranges. Fluorescence efficiency rises as sunlight strengthens, then levels off when photodissociation starts beating production. That is why comet colors and brightness curves can look jagged as different ices with different boiling points take turns driving the show. We can model this with simple physics and test it against what the next observing window reveals. If the green obeys the rules of sunlight and gas production, natural chemistry holds. If it refuses to behave, we begin a different conversation with data in hand. So the green is a message, not a verdict. It says the coma is active. It says carbon chemistry is alive near the nucleus. It says the sun is writing on a cloud of molecules that barely exist, yet glow with enough coherence to reach our eyes across millions of kilometers. It is not proof of anything beyond that. It is a reason to watch closely, to compare before and after, and to keep our instruments honest. Let beauty pull you in, then let measurements tell the truth. When light is peeled into its hidden stripes, atoms start to talk. 3I, Atlas, has been speaking a curious dialect. Several teams reported nickel shining clearly in the spectrum while iron stayed, quiet, or whisper, faint. That pairing is upside down compared with what we expect. Across meteorites, asteroids, and many familiar comets, iron and nickel are cousins that travel together in steady proportions forged long ago in stellar furnaces. So, when nickel stands on the stage alone, people sit up straighter. Is the chemistry unusual? Is the temperature regime special? Or is our instrument angle playing tricks? Spectroscopy turns glow into fingerprints. Heated or sun-struck atoms emit sharply defined colors that act like name tags. The surprise here is not that nickel exists. Trace metals appear in Comet Comet more often than most headlines admit. The surprise is the imbalance. Nickel lines pop with confidence. Iron lines do not. Before anyone reaches for exotic explanations, we run through the more grounded reasons that nature might skew the script. Temperature and excitation come first. Different atoms light up efficiently at different combinations of temperature, density, and sunlight. If iron needs a little more kick to glow in the visible band while nickel can radiate under cooler conditions, then a coma with patchy heating can tilt the signal toward nickel without changing the true bulk composition. Ionization states matter as well. If iron is sitting in a charged state whose best lines fall outside our observing window, we will miss it, while nickel rings the bell right where our spectrographs listen. Chemistry and structure add another set of levers. Nickel can hide inside fragile compounds that break apart sooner than iron-bearing minerals. As the sun turns up the heat, imagine outer layers layered like an onion. The most volatile ices and the most delicate molecular cages surrender first, releasing nickel in a form that glows. Iron bound inside tougher grains may require deeper heating or stronger sunlight to participate. Space weathering over a long interstellar cruise can also coat and alter surfaces. Grain sizes evolve. Surfaces darken bonding. Environments change. Any of these can bias, which atoms step forward when the coma wakes. Dust physics can fake a composition change without changing the mix at all. Small grains get pushed and heated differently than big grains. If the coma is briefly dominated by one size class, the lines we see can swing for a few days before drifting back toward balance. Add rotation of the nucleus, and you have a recipe for short-lived asymmetries. A jet tied to a metal-enriched patch rotates into sunlight, and the spectrum tilts A. Few hours later, the jet turns away, and the tilt softens. What felt like a single shocking truth becomes a snapshot of a moving target. Now place the metallic puzzle into the wider chemical portrait that instruments have painted so far. James Webb Space Telescope observations at larger distances suggested that carbon dioxide was driving early activity while water stayed. Mostly locked down, that pattern is common for cold visitors. Carbon dioxide wakes at lower temperatures. Water waits for closer runs to the sun. Hubble-class imaging and modeling keep the nucleus modest in size, only a few kilometers across, which favors a small number of active areas rather than a global eruption. All of that frames a scene where chemistry arrives in layers. Volatile gases lead the parade. Dust and tougher species join later. It is important to remember what we are not seeing. We do not see steady non-gravitational acceleration that would scream continuous thrust. We do not see coherent radio tones that would betray transmitters. We do not see thermal patterns that demand internal power. Spectral lines with an odd ratio do not leap across the line from exotic natural to engineered. They simply tell us the coma is a more complicated chemistry lab than a tidy diagram suggests. There is a social rhythm to these detections that we should name out loud. Preliminary reports ripple across the internet before the slow grind of peer review sorts out calibration, background subtraction, and confidence intervals. In that time gap, nickel without iron turns into a myth. The antidote is boring and strong. Repeat the measurement with different instruments. Observe over multiple nights to see how stable the ratio is. Cross-check against reference stars and lamps. Look in the near-infrared, where different iron lines may live. If the signal survives that gauntlet, Then we upgrade the puzzle from curious to robust. Agencies have been clear and useful in their tone. Natural remains the leading frame. Even when the details are exotic, European and American teams highlight how tiny changes in temperature and photochemistry can swing line strengths. They also point out that our sample of interstellar visitors is tiny. One interstellar rock and one interstellar comet before this one do not tell us what normal looks like for a population born around other stars. 3I Atlas may be our third data point in a set that will redefine expectations rather than violate them. What would make the metallic story truly jaw-dropping? A consistent absence of iron across many wavelengths and many dates, even as sunlight grows stronger, would be strange. Isotopic ratios, far from solar norms, would raise eyebrows. A metallic signature that turns on and off at crisp intervals, unrelated to rotation or solar input, too, would also be odd. We do not have that. We have a bright nickel voice and a quiet iron voice, recorded during specific windows while geometry and glare. They were changing fast. The best part of this puzzle is how testable it is after the blackout. As 3I Atlas swings past its closest solar distance and the coma chemistry changes, iron should become easier to excite if simple heating was the limiting factor. If iron lines strengthen while nickel holds steady, the imbalance fades into a timing effect. If nickel fades and iron remains elusive, then we push harder on microphysics, grain evolution, and odd bonding environments. Either way, we move from debate to comparison, which is where science cashes its checks. So, let the metal lines keep their mystery a little longer, but do not let them kidnap the whole story. A green glow tells us carbon chemistry is alive. Carbon dioxide led the early wake-up. The nucleus is small and likely patchy, which makes temporary spectral tilts likely nickel without much iron is a headline that fits that patchy layered world. It is a signal to watch, not a verdict to carve in stone. When the glare lifts and the lines return, we will see whether the dialect of metal settles into something familiar or keeps its strange music. Either way, we will have learned how to listen better. Let us answer the nervous question cleanly and early. Are we in danger? No. Both travelers are photogenic and scientifically rich, but their paths keep them comfortably far from Earth. 3I Atlas never comes closer to us than roughly 1.8 astronomical units, which is about 270 million kilometers. Its nearest point to the Sun is around 1.35 astronomical units. Just inside the orbit of Mars, SWAN R2 sweeps closer in a way that feels dramatic to the eye, yet remains safe to the bone. Its closest pass to Earth is roughly 0.27 astronomical units, to about 40 million kilometers. That is close enough for pretty pictures and far enough to sleep well. Here is the plain language test professionals use when headlines get spicy. Can the orbit of the object and the orbit of Earth be in the same place at the same time? If the answer is no, by a wide margin, the story ends there. The distance of closest approach, sometimes summarized by a minimum crossing number, stays large for both visitors. Even if small non-gravitational nudges from venting gas tweak the path, there is so much room in the geometry that the safety verdict does not change. Brightness is not menace. A comet with a broad, camera-friendly tail can look enormous and feel near. That tail is a whisper thin cloud of dust and gas spread across gigantic volumes of space. You could drive a planet through it and barely notice. The ion tail that points away from the sun is even thinner, a filament shaped by the solar wind. It is wonderful for photography and physics, and useless for drama about danger. If SWAN R2 paints a long brushstroke across October skies, and that means the viewing angle is kind and the dust is scattering sunlight, well, it does not mean the material is headed for us. 3I Atlas carries a different anxiety for some viewers because it is interstellar and because it moves fast. Interstellar simply means unbound to the sun. It does not mean targeted. The hyperbolic path is a pass through our neighborhood, not a homing line. Fast does raise kinetic energy in the abstract, but kinetic energy matters only if two things meet. These do not. The numbers are not close calls, they are big cushions. You may hear about a near-Mars moment and wonder whether that hints at a chain of risk. Early October places 3I Atlas, tens of millions of kilometers from Mars. That is an astronomer's way of saying close enough for spacecraft to try a look, and far enough to be routine. Gravity from Mars will not whip the object anywhere dangerous. The laws that steer small bodies are well known. Teams compute many possible paths that bracket all reasonable outgassing effects, and then report the corridor. The corridor misses us by a country mile on the scale of the inner solar system. Another common worry involves debris. People imagine fragments, meteor storms, and surprise showers. Fragmentation can happen to comets, especially after tight solar passages, but distance rules apply here too. SWAN R2 does not cross our orbit in a way that sprays fresh dust into our path. 3. I-Atlas never approaches Earth at all. The radiant glow is not a forecast of grit in our atmosphere. It is light, bouncing off dust and gas already nowhere near us. If there were even a slight chance of hazard, the International Monitoring Machine would behave differently. Planetary defense teams exist to model, update, and alert. They publish risk tables for objects that pierce certain thresholds. That system gets twitchy for genuinely concerning geometries. It is calm now, because the math is dull in the best possible way. The orbits are far, the angles are friendly, and the uncertainties remain small compared with the large margins. So what should we pay attention to? If not personal safety, pay attention to the opportunities. Safe distance plus unusual chemistry makes the perfect laboratory. A green tint from carbon molecules and cyanogen tells us about photochemistry. Nickel lines without strong iron invite a deeper look at grain physics and temperature. SWAN R2's evolving tail lets us see solar winds sculpt a ghost. None of that changes our daily lives directly. All of it changes how well we understand the environment that made deafen those lives possible. If you want a human-scale picture, think of a lightning storm you can watch rolling across a valley at night. It is powerful and a little eerie, and you can enjoy it because it is far away. The distance does not drain the meaning, it delivers it. We are witnessing a rare double act with 0 threat tags attached that lets us be curious without flinching, which is the best mindset for science and for wonder. Picture the story shifting to a different balcony. While Earth's view narrows into glare, Mars sits off to the side like a quiet theatre box with a clean sightline. Early October brings 3i Atlas past the red planet at a distance that sounds grand on paper, yet opens a small but precious window for science. We are talking tens of millions of kilometers. That is far for postcards and close enough for disciplined measurements. It is the right distance for a few sharp questions and maybe a couple of crisp answers. Mars is not empty. It carries a small fleet of diligent machines with excellent eyes. The Trace Gas Orbiter carries spectrometers designed to sniff faint gases above Mars, which also makes them capable of sampling light from a comet's coma. When pointed outward, Mars Reconnaissance Orbiter holds a famously sharp camera that maps Mars in stunning detail. It cannot resolve a nucleus at this range, yet it can measure how the coma spreads and how brightness changes across pixels. Mars Express adds imagers and spectrometers that have watched auroras and tenuous clouds. Those same tools can sketch a comet's ion tail when geometry cooperates. The advantage is angle. From Mars, the line between Sun and comet and observer is not the same as Earth's. That different phase angle changes what shines and where dust grains scatter sunlight in patterns that depend on their size and texture. Seen from one angle, the coma looks like a soft sphere. Seen from another, it develops gradients and bows that reveal how big the grains are and how strongly they clump. If images from Mars show a stronger forward glow than our Earth-based shots did, that is a hint about grain sizes. If the ion tail points at a slightly different angle from Mars than from Earth, parallax lets us triangulate its true direction in the solar wind. There is also timing. 3i Atlas is warming fast as it slides toward late October. Volatile ices are switching on in layers. That is exactly when subtle jets begin to carve patterns in the coma, and when the ion tail becomes more structured and sometimes fragile. A disconnection event can rip the tail like a ribbon when magnetic fields snap and reattach. From Earth, we could miss that drama in the glare. From Mars, we might catch the moment the tail detaches and reforms. Even a simple sequence of short exposures can turn into a time-lapse that ties behavior to solar wind conditions. Limitations keep the promise honest. Mars orbiters are built first for Mars. Their pointing rules, exposure, limits, and data rates are tuned for a planet beneath them, not for faint objects, millions of kilometers away. Teams must pre-plan a narrow sequence, execute it without real-time steering, then downlink the results on the next communication window. The comet will be a small blur, a few pixels across, not a resolved world. Spectra will be faint and may mix with background stars unless the sequence includes careful background frames. Still, the measurements matter because they lock the physics to an independent vantage point. What can a handful of pixels tell us? More than you might think. A slightly elongated coma profile that matches the direction of motion points to dust being shed more strongly in that direction. A brightness peak that shifts over hours implies rotation of an active patch on the surface. A change in the slope of the brightness curve, with distance from the center, reveals how the size distribution of grains evolves as sunlight pushes small grains faster than large ones. If the spectrometers see a bump where carbon dioxide lines should be, that supports the story that early activity is driven by that gas rather than water. If hydrogen glow strengthens later, that hints that water finally woke up. There is one more gift in a Mars view that numbers alone cannot explain. It is the ability to overlap data from different instruments and stitch a fuller scene. A Mars-based image that shows the dust tail direction can be paired with a solar instrument view of the corona to infer the wind that shaped it. A spectrum that catches a weak line can be checked against Earth-based spectra from earlier nights to track the rise of a molecule day by day. Even the absence of a feature is useful. If Mars sees no ion tail during a period when Earth-based solar monitors report a strong stream, that mismatch teaches us about how the comet's outgassing responds to changing space weather. The balcony metaphor also applies to risk. Observing from Mars means we are not pointing delicate Earth-based mirrors too close to the sun. It buys safety margin and scientific margin at once. We can run the same small test across multiple orbits. If a storm or a glitch ruins the first attempt, we can treat every clean detection as another knot in the rope that connects the before and after of the glare. The poetry here is practical. A visitor from another star brushes a planet we have explored with robots for 2 decades. Those robots glance up from their routine to watch a traveler pass. They cannot wave, and the traveler would not notice if they did. Yet the measurements they take will help us decide whether this was simply a lively ice body or something stranger. The balcony does not deliver a front row seat. It delivers a different angle on the same play, and sometimes that is the angle that makes the plot click. So when Earth begins to squint and the instruments go quiet, keep one ear tuned to Mars. Expect short sequences, not glossy reels. Expect modest signals, not dramatic reveals. Expect numbers with error bars that still move the conversation from maybe to likely. The red planet will not solve the whole puzzle. It may hand us the thread that ties the act before the blackout to the act after. In a month built on timing, that thread could be worth more than any perfect picture. Picture the evening sky turning cobalt while streetlights flicker on. Low in the west, a faint fan begins to lift off the horizon. At first, it looks like a smudge that refuses to focus. Give your eyes a minute. The smudge sharpens into a pale wedge leaning away from the sun. That is SWAN R2, taking a bow. It is not a singular star that pierces the dark. It is a cloud made of countless dust, grains, and gas molecules, all pushed and pulled by sunlight and the solar wind, until the whole thing behaves like a luminous windsock. SWAN R2 spent weeks sneaking along the line of the sun, hidden by glare. The moment the angle widened enough, it seemed to appear, fully formed. That quick entrance is normal for comets that approach from the blind side. The inner curve of its path carried it to about half an astronomical unit from the sun in mid-September. Heating turned frozen gases into jets. The jets dragged dust into space. Dust scattered sunlight. A tail was born. As October progressed, Earth moved into a nicer viewing geometry. So, the comet felt like it was brightening faster than any chart predicted. Part of that change is real outgassing. Part is simply better angles. Here is how to watch without any special gear. Go out soon after sunset with a clear view of the western horizon. Bring patience. The sky needs to darken enough for the contrast to pop. If you can step away from city light for even a few blocks, do it. Your eyes will reward you. A simple pair of binoculars makes a surprising difference because it gathers more light and steadies the image. Sweep slowly just above the fading glow. Once you pick up the head, ease the view upward, and you will see the tail flowing away from the sun like a smoke plume turned to glass. Do not expect neon. Human vision under low light prefers contrast to color. cameras will show richer tones than eyes. What matters for you is shape. The dust tail often looks broad and soft. Sometimes a thinner, straighter ray will point almost directly away from the sun. That is the ion tail. It is made of charged gas riding the solar wind. On some nights you may notice a faint kink or even a break in the narrow tail. That is a disconnection event. When magnetic fields snap and reform, it is subtle. It is also one of the most alive things you can see with a simple setup. The comet's brightness will dance. Do not let that throw you. Comets are messy engines. Different ices take turns driving the show as distance and sunlight change. The surface rotates so new vents come into view while old ones fade. A burst of dust can lift the whole coma for a night and then settle. Think of it as weather on a tiny world with no air, where sunlight is the only throttle. Your notes will matter more than you think. If you jot down a quick line about how large the coma looked in your binoculars and which stars the tail passed near, you are doing citizen science that helps turn individual impressions into a shared record. If you can see the comet over several evenings, try a small ritual. Stand in the same place, start at the same minute after sunset. Count how long it takes before the head becomes obvious. That simple timing is a proxy for brightness. If the number of minutes falls night by night, the comet is brightening in your sky. If it rises, the comet is fading, or the geometry is getting worse as it slides lower. You do not need a catalogue to make it meaningful. You need consistency and curiosity. Safety deserves one clear reminder. Never scan too close to the sun with optics. The best views happen after the sun is well below the horizon, and the sky has taken on that deep blue that comes right before full night. Give the sun a generous buffer. Comfort also matters. Bring a light jacket, a chair, and a friend. The show rewards unhurried attention, and it is more fun with someone to point and wonder with. For photographers, a tripod and a short exposure around a few seconds can reveal the tail in dramatic length. Take a sequence across several minutes. Later, you may spot motion you missed while staring at the screen. A small change in the angle of the tail can betray a shift in the solar wind. A mild brightening of the head can mark a jet turning into sunlight. You will not resolve the nucleus, but you will catch the dance around it. SWAN R2 is a gift because it is both kind to beginners and generous to obsessives. It gives casual viewers an easy win and gives careful watchers a nightly puzzle. It is not a comet that demands a remote desert or a giant telescope. It asks for a little time while twilight deepens, and for the willingness to look twice, first to find it, then to notice how it changed. The best part is knowing that your view is one frame in a planet-wide time-lapse. Someone south of you will see the tail at a slightly different angle. Someone with a spectrograph will see the gases as coloured lines. Someone else will compare all of that to the sun's wind. At that moment, when we stitch those frames together, SWAN R2 becomes more than a pretty wedge in the west. It becomes a moving experiment that teaches us how ice, rock, sunlight, and plasma write temporary shapes across the sky. Watch the fan lift, watch it thin, watch it bend. It is the most patient kind of drama, and it is happening right over the evening commute. If you've ever watched a kettle before the boil, you know, the rhythm of a comet, quiet, a tremor, then bursts that feel almost alive. The difference is that a comet has no liquid to simmer. It lives in vacuum, where ice does not melt into water first. It turns straight from solid into gas. That jump is called sublimation, and it is the engine behind every halo, every plume, every lopsided tail you have ever seen in a photograph. The sun is the throttle. As a comet drops inward, sunlight hammers the surface, and heat seeps down only a few centimeters before radiating away. That thin layer is the thermal skin. Within it lie pockets of frozen gases with different personalities. Carbon dioxide and carbon monoxide are eager and volatile. They begin to flow far from the sun when temperatures are still bitterly cold. Water is shy by comparison. It waits until the comet is much closer before it can switch on. When the eager gases wake first, they carry dust with them and sketch a faint coma long before water has a say. Now add rotation, and the surface gets interesting. A comet is not a smooth sphere. It is a lumpy world with cliffs, pits, and crusts of dust that act like quilts over the ice. As the nucleus spins, the sun lights one patch, then another. Vents facing daylight gasp, Vents in darkness quiet down. The light we measure from Earth rides that daily rhythm. So the brightness curve picks up wiggles that look like someone is tapping a power button. No machinery is required. A rocky snowball that turns like a slow hour hand will do. Thermal lag creates another trick. Even after a patch rotates into sunlight, it takes time for heat to soak down to the ice and for the gas to punch through pores and cracks. The result is a delayed puff that peaks after noon in the local time of that patch, when the same region rotates back into darkness. It can keep breathing for a while before falling off. Layer this delay across several active areas, and the global output looks jagged, like a heartbeat seen through fog. Surface mantles complicate the show. As gas escapes, it drags grains of dust upward. Fine grains flow easily. Large grains tend to fall back and settle into a blanket that insulates the ice beneath. That blanket muffles activity until sunlight or a small collapse opens a fresh path. Then, production can spike, sometimes dramatically. We call those jumps, outbursts. They are not explosions in the action movie sense. They are sudden openings in a crust that let pressurized gas and dusty frost rush outward for a few hours or a day. Because each volatile wakes at a different temperature, the mix of gases changes with distance from the sun early on. Spectra lean toward carbon-rich signatures, and the coma may look greener as diatomic carbon and cyanogen do most of the glowing. Closer in, the fingerprint of water grows, and hydrogen maps from solar observatories begin to sing. After perihelion, as the comet recedes and cools, the activity can sag, or sometimes a warm layer buried deeper can take over and keep the coma fuller than you expect. Every comet writes its own schedule on this theme. The jaggedness is not only in the physics, it is also in the geometry of how we watch. At some phase angles, dust throws sunlight forward toward us, and everything looks brighter than the raw gas production would suggest. At other angles, the scattering is less efficient, and the same output looks subdued. A small change in angle can mimic a physical surge or slump. That is why observers always log the angle along with the light. We want to separate real changes at the source from the tricks of vantage. Non-gravitational forces are the quiet consequence of all this venting. When a jet blows harder on one side than the other, it nudges the nucleus like a tiny thruster. Over weeks that can shift the path by small but measurable amounts, it can also change the spin rate, shortening or lengthening the day by minutes. Teams try to catch these shifts by comparing the observed positions to the predictions and by tracking periodic flickers that reveal rotation. If 3i Atlas or SWAN R2 seem to breathe in time with a spin that is slowly changing, that is outgassing torque doing its work, not a steering wheel. How do we turn this chaos into a forecast? With models that follow simple rules, brightness tends to scale with distance from the sun by a power law that steepens when fresh ices wake and flattens when mantles choke the flow. Gas production ratios slide in predictable. Directions as temperature rises, light curves pick up, repeating wiggles if rotation dominates but show single night spikes if a crust breaks. None of these rules is perfect. Together, they give us a checklist. When the glare ends, if water lines grew as expected, if carbon dioxide relaxed, if the wiggles repeat with the same beat, the natural picture wins. If the light ignores distance, if the lines switch on and off at clean intervals unrelated to spin or sunlight, then we point and say, show that again. Citizen science fits right here. Backyard logs that mark when the head becomes obvious after sunset. Simple sketches of tail width. Even color impressions noted consistently night after night. All help stretch the curve across gaps. Professionals, we can then fold those notes into photometry and spectra to extract the underlying physics. The more eyes we bring, the smoother the jagged edges become when we average them into a pattern. So when you see a sharp rise in brightness or a sudden change in color, do not rush past the obvious explanation. A new patch of ice may have rotated into dawn, a dust blanket may have slipped, carbon dioxide may have seeded the lead to water. Nature is fully capable of drama. Your job and ours is to listen for rhythm in the noise, to test the beat against distance and spin, and to let the light curve teach us how these small worlds wake. When the two visitors return from the glare, their jagged lines will not be flaws, they will be signatures. Two strangers arrive on one stage, and our storytelling brains start sketching choreography. But what if the script is just statistics with good lighting? The universe throws dice with more sides than we can imagine, and it rolls them for billions of years. Given enough throws, rare alignments stop being shocking and start being expected somewhere, sometime. The trick is learning how to keep wonder alive while letting math take the wheel. Begin with the law of large numbers in plain clothes. If a tiny chance event can happen on any night across the whole sky, add up all the nights and all the sky, and the chance of at least one such event rises. Add modern surveys that watch more of the sky more often, with deeper sensitivity, and you increase the number of tickets in the cosmic raffle. Suddenly, a once-in-a-lifetime coincidence becomes a once-in-a-generation sighting. Not because the universe changed, but because we started paying attention with better instruments and better coverage. Now fold in selection effects. We notice what we can see. Comets that sneak along the sun's glare line remain invisible until geometry improves. When they step into twilight, they look like they arrived fully formed. The calendar then feels packed because the visible window is packed, not because the physical events truly stacked up. This bias has a name in observatories and a simple meaning for the rest of us. The sun hides things until it does not, then they pour out together. There is a cousin to selection called survivorship. Quiet, ordinary apparitions pass without headlines. The few that are bright, green, fast, or conveniently timed become famous. Our memory keeps the loud ones and lets the quiet ones fade. When we compare a shelf of loud stories, clustering leaps out, even if the full shelf of all stories is smooth. The cure is to count all cases, not just the hits that made us feel something. Humans also slip on a classic mental banana peel. We underestimate how often coincidences happen when many trials are running in parallel. The birthday puzzle is the friendly example. In a group that is smaller than your gut expects, a shared day appears with surprising frequency. The sky plays the same trick. Hundreds of objects are, moving on different schedules. The chance that 2 or 3 milestones land in the same month somewhere is much higher than the chance that 2 specific objects meet on a specific date. Our brains compute the second number when the first number is the one that matters. Does that mean there is no pattern worth chasing? Not at all. It means we need rules that separate meaningful structure from the noise we are built to adore. Rule 1 is predictive power. A real pattern lets you forecast a next beat that later shows up on time. Rule 2 is mechanism. A pattern worth naming should sit on a physical explanation that changes numbers, not only stories. Rule 3 is replication. If we see the same rhythm across different objects under different conditions, the case grows teeth. Apply those rules to our October pairing. The overlap is visually dramatic and historically rare, yet it does not, by itself, predict a new arrival or a repeat. The geometry and discovery biases explain much of the timing. The mechanism we can test is ordinary comet physics plus survey cadence, not secret coordination. Replication will come with future visitors. If the next decade delivers repeated double acts with similar spacing and similar chemistry, eyebrows will rise for good reason. If not, we will file 2025 under great month in the annals of comet watching and carry on. There is a deeper reason to practice this kind of thinking. It protects the wonder. When we understand why coincidences happen more often than our intuition allows, we stop being yanked around by every alignment, and we save our amazement for the outliers that survive hard checks. That is not cynicism. It is care. It keeps curiosity sharp rather than dulled by too many false alarms. So how do we hold both feelings at once? We let the spectacle do its work. We allow the double act to feel like a gift. Then we sharpen the pencil. We track how survey reach has expanded. We count nights with useful elongation. We compare with past decades using the same rules. We ask the unpopular question about how many near misses never made the news. The answer to that question often drains the mystery from an apparent surge, and that is exactly what makes the remaining mysteries shine brighter. There is one more human element to acknowledge. Stories are how we share attention. A coincidence is a story engine with the key already in it. That is fine, as long as the engine powers observation rather than fantasy. If the tale brings more eyes to the sky and more logs to the databases, it has served the science. If the tale begins to demand conclusions the data does not support, pull back and reset the terms. The sky is patient. It gives us more chances than we deserve. Here is the balance we will keep as the month unfolds. We will celebrate the timing with clear eyes. We will model the selection effects that make the calendar feel haunted. We will resist the urge to promote coincidence into cause, and we will stay ready to change our minds if the next measurements refuse to fit the null. Fate is a feeling. Pattern is a test. The more we honor that difference, the more satisfying the answers become when the light returns. If one of these visitors were a machine, the sky would leave fingerprints. Gravity writes, smooth curves. Engineering writes, corrections. Our job is to list the signatures that real hardware cannot help but produce, and then check whether the data shows any of them. Curiosity stays. High standards stay higher. Start with motion. Natural bodies follow paths fixed by gravity, unless sunlight and gas jets nudge them a little. Those nudges rise and fall with heat and with rotation. Engineering looks different. Thrust wants a direction and a plan. In the numbers, that means a steady push that does not care about day or night on the surface. It means an acceleration that holds a line for hours or days instead of wobbling with spin. Fit the trajectory across many nights. If the residuals point one way, like a quiet wind that never turns, that smells like propulsion. If the residuals breathe with sunlight and rotation, that smells like outgassing. Now, look for attitude control. Real vehicles point things on purpose. Antennas, radiators, sensors. Purposeful pointing makes light curves blink in patterns that repeat like a metronome, even when the viewing angle and the solar input do not demand it. A machine might also roll to spread heat, or to keep a radiator away from the sun. That roll would stamp a crisp rhythm onto the brightness, independent of the messy beats of vents and dust. Nature can repeat too, but it ties its rhythm to day length and distance. Engineering repeats, even when the sun and the distance change. Listen next. Coherent radio is a tell that almost nothing in nature fakes. Space is loud with broadband hiss and with natural burst from the sun, but narrowband tones that hold a razor-thin frequency and drift only with simple motion are the province of transmitters. Radio telescopes hunt for that tone in bands where an intelligent builder might hide a beacon or a link. If something sings with a clean line and the drift matches the Doppler of the object only, not the weather of space, ears perk up fast. Shine radar at it. Metal and complex structures bounce radio in distinctive ways. Natural comets tend to eat radar and return whispers because fluffy dust and ice are poor mirrors. A sharp echo would surprise everyone. Even a weak echo with strange polarization could raise eyebrows if it refuses to match the textures that ice rubble should produce. Distance makes radar hard. The method still belongs on the list because a single bright ping would rewrite the story. Heat tells tales. A machine manages temperature that demands surfaces that radiate in controlled patterns. Natural bodies warm and cool with the sun and tumble their hot and cold patches into view. Infrared telescopes can tell the difference. A thermal map that follows sunlight feels right. A thermal map that holds fixed hotspots through changing geometry feels wrong. Energy budgets bite here too. If an object radiates more heat than sunlight can supply, where is the extra power coming from? Spectra can betray design in quieter ways. Exotic alloys and coatings leave narrow atomic lines at odd strengths. Unusual isotopic ratios can stand out if they land far from solar norms. Even gases can carry structure if they are being expelled through nozzles rather than drifting from porous ice. A jet driven by engineering might produce a narrow, collimated plume with constant speed. Sublimation produces broader flows that change with rotation and with how sunlight hits rough terrain. High cadence spectra across a night can separate the two. Dust behavior gives another angle. Vents on a natural surface sputter and surge. They follow cracks and pits and inherit the chaos of geology. Engineered emission like symmetry. A pair of opposing plumes to cancel torque. A fan that holds a constant opening angle across hours. If processing reveals tails and jets that keep a precise geometry while the nucleus rotates, the suspicion grows. If structures twist and fray as the body turns, nature keeps the lead. Search the neighborhood for companions. Hardware loves helpers. A courier might shed small coasting parts that hold formation. A relay might keep station a fixed distance away. Natural fragments wander. Engineered escorts. Station keep precision. That means measurable differences. Track the separation in images. If it stays constant beyond what gravity and pressure would allow, the case strengthens. Timing is a final truth serum. Natural spikes trace sunlight, a surge when a vent rotates into dawn, a lull after local dusk. Engineering often ignores such schedules and obeys mission clocks instead. A 20-minute pulse every few hours that repeats across changing distances would punch through the noise, so teams fold the light, curves, and the spectra on many trial periods to look for clocks. So far, nothing crisp. Stack all these tests, and you get a simple scoreboard. Constant non-gravitational acceleration that cares little for rotation would be a point for engineering. Coherent radio would be a giant point. Radar echoes stronger and cleaner than ice. That should allow would be a point. Thermal power beyond sunlight would be a point. Fixed geometry in dust, despite rotation, would be a point. Companion pieces that hold distance like dancers would be a point. A repeating clock that ignores the sun would be a point. What do we have today? We have accelerations that track sunlight and spin. We have brightness curves that dance with rotation and distance. We have spectra that favor common molecules, and a few odd line ratios that can live inside complicated ice and dust. We have no clean tones on the radio. We have no thermal excess that demands a power plant. We have no station-keeping companions. That does not prove absence forever. It does say the sky is acting like sky. The value of this checklist is not to kill wonder, it is to protect it. If some future frame reveals one of these hard tells, we will all know what it means in the same breath. Until then, let the machines in your head stand by, while the machines on our hills and in our orbit keep measuring. Nature can put on a show that looks engineered. At first glance, the second and third glances are the ones that separate a miracle from a mechanism. Let us borrow the imagination for a few minutes and give it rules. If intelligence were involved, how would two very different travelers choreograph a shared mission around our star? We will sketch 3 ideas that science fiction loves and science can test. A nimble scout with a larger fortress, a maintenance run on a cosmic timetable, ancient patrol that watches civilizations as they light up the radio sky. None of these needs to be true to be useful. Each becomes a lens that sharpens what to look for when the glare lifts. Start with the scout and the fortress. Picture 3-eye Atlas as the courier, small, fast, and optimized for reconnaissance. Picture SWAN R2 as the base, big, power-hungry, and suited for storage or relay. If that pairing were real, coordination would show up as timing that serves the exchange rather than the sun. 3 predictions follow. First, rendezvous geometry would matter more than perihelion geometry. We would expect synchronized peaks in activity near a shared corridor rather than at each object's own thermal maximum. Second, the smaller craft would show orientation patterns that favor a fixed bearing relative to the large one, even as both move around the sun. That would leave a subtle rhythm in light curves that does not match simple rotation or solar heating. Third, both objects would display matched anomalies close in time, like twin surges or twin lulls, separated by a consistent offset that fits a message or material handoff. In data terms, we would look for cross-correlation between their brightness and spectral changes after removing the effects of distance and angle. Now try the maintenance run. Imagine an automated network that services hidden infrastructure around stars on cycles longer than civilizations. 3-eye Atlas could be the diagnostic probe that sweeps past to map conditions, and flag work orders, SWAN R2, could be the slow truck that carries bulk parts or energy devices, disguised as natural coma physics. A maintenance script would carry signatures of routine. The predictions get specific. We should find schedules that repeat across decades. When archival data is deep enough, we should see behavior that fits standardized phases like survey, transfer, and depart, each with characteristic durations that ignore the messy individuality of comets. Even chemistry might reflect procedure. If the same sequence of gas ratios appears before and after a putative service window, that smells like a checklist. In practice, observers would build a timeline from every spectrum and every light curve, then test whether transitions cluster near integer multiples of some cycle measured in days or weeks, rather than at distances where molecules naturally switch dominance. Now, the ancient patrol, suppose long-lived watchers sweep the inner system to check any world that has started leaking radio noise or laser flashes. Our broadcasts have carved a sphere roughly 100 light-years wide, So a patrol might drift through to tag and sample. The testable claim is not romance, it is targeting. A patrol that cares about Earth would optimize for our vantage lines. That means activity spikes when the object sits at angles that favor views of our transmitters and orbital lanes, not when the sun demands chemistry. Another prediction involves assets. The patrol would prefer multiple small platforms over a single spectacular one, because redundancy beats heroics in old systems. That would to produce faint companions that hold formation. If we ever saw a pair of dim knots keep steady distance from a bright ahead while the tail flutters, the patrol idea would earn a longer look. Each scenario arrives with failure modes that rescue us from wishful thinking. The Scout and Fortress story fails if every flare lines up with simple solar heating, and if any crosslinks vanish after we correct for geometry. The story fails if timelines refuse to snap to any fixed cadence, and if gas ratios follow the smooth arcs that natural sublimation predicts. The patrol story fails if searches for quiet companions turn up nothing, and if every brightness change bows to rotation and angle. Failure is not a mood. It is a filter that keeps imagination honest. There are practical ways to probe these ideas without pretending we can see secret machines. For the Scout and Fortress test, we compute residuals after removing distance and phase effects from both visitors, then slide. One time, the series passed the other to look for a lag that repeats. Real coordination would leave a ridge of correlation that holds for days, not a single night. For the maintenance test, we fit a simple 3-state model to the light curves and spectra, then ask whether the preferred transition times share a common ratio. If the best fit ratios wander with geometry, the scenario fades. If they cluster around a fixed ratio, with tight error bars, eyebrows go up. For the patrol test, we stack deep exposures to search for faint co-movers that hold position within narrow bounds through rotation and changing angles. Natural fragments drift and spread. Station keeping does not. We also borrow the sun itself as a referee. Any technology that pretends to be cometry will still have to swim through solar wind and magnetic field changes. That means tail kinks, disconnections, and ion behavior should line up with the space weather bulletin, regardless of motive. If a structure resists those forces while nearby structures do not, we have an oddity worth chasing. If everything dances when the wind snaps, camouflage wins, and nature takes the credit. There is a humility built into this exercise that matters. Extraordinary claims pay rent only when they make new predictions that survive contact with fresh data. Our thought experiments have now paid that rent with a handful of simple walled checks that the coming months can deliver. None demands exotic hardware. They demand clean baselines before the blackout, disciplined comparisons after, and a willingness to publish null results as loudly as flashy ones. The reward is clarity. If coordination and mission clocks refuse to appear, the stories go back on the shelf, and the comets stand taller as natural wonders that fooled our pattern-hungry minds for a season. And if one of the tells peaks above the noise, even faintly, the follow-up writes itself. More cadence, more angles, more telescopes pointed in concert the Scout and Fortress would need to keep sinking. The maintenance run would need to keep its schedule. The patrol would need to keep its formation. A single odd night is a spark, a repeating oddity is a case. Either way, we win. We learn to test better stories with better discipline, which is how curiosity grows teeth. Imagination is a tool, not a verdict. So let us take 3 of the boldest stories people tell about strange visitors and turn them into checklists that real data can hit or miss. The relay hypothesis says a courier arrives from interstellar space to drop information into a local processor that hides as a comet. The harvest scenario pictures stellar skimmers that mask industrial collection systems behind ordinary coma physics. The conflict play imagines rescue, retrieval, or purge operations staged behind the sun's glare. None of these claims changes what the telescopes see. Each one proposes patterns that must show up if the story is more than a mood. Start with the relay. A courier delivers, a hub transmits. If that choreography were real, energy would peak when transmission is easiest, not when sunlight alone says the chemistry should roar. Look for activity spikes that align with windows when geometry favors communication paths rather than perihelion. In practice, that means a rise at specific angles to the sun that repeat as both objects move, or surges, keyed to the 27-day rhythm of solar rotation. If a gravitational lens or plasma conduit is part of the scheme, the second tell is synchronization. The courier and the hub should show paired anomalies with a consistent lag and a consistent order: courier first, hub second, or the reverse: strip away distance and phase effects and run a sliding correlation between their light curves and spectral lines. Real coordination would leave a ridge that persists across nights. The third tell is narrowband leakage. Information systems hate waste, but perfect stealth is hard. Radio and optical searches would hunt for faint tones or line width narrowing that sit on top of normal coma lines. A single clean carrier that drifts only with the object's motion would bend this hypothesis toward the serious. Now, the harvesters, nature already produces elegant plasma funnels and dust flows, so the bar here is high. An engineered collector would need to do what sunlight and solar wind cannot. The first tell is non-Keplerian station. Keeping near the sun, natural coma structures stream away. Collectors would hold geometry as the nucleus rotates, map the jet angles across hours. If a fan holds the same opening angle and orientation despite rotation and changing phase, suspicion grows. The second tell is unearned. Power. Harvesting implies conversion. A steady thermal excess beyond what sunlight can supply would be hard to hide if collection were significant. Infrared light curves checked against solar input become a ledger. The third tell is composition that resists ordinary sublimation logic. Industrial processing would fractionate elements and isotopes in ways that do not match the gentle sorting of heat and photochemistry. If post-perihelion spectra show exotic isotopic ratios or metals in patterns that stay constant while heat and distance change, we would be forced to ask why a natural coma keeps returning the same refined mix. Finally, the conflict play. Rescue, retrieval, or purge. Drama demands decisive signatures. A rescue would favor approach and proximity. That means trajectories that bend toward each other at the same timescale, not merely pass through similar longitudes weeks apart. Precision matters. Closures to constant separation rather than quick crossings. A retrieval would leave the smaller object dimmer or fragmenting, while the larger brightens in step, with shared dust structures that overlap in velocity space. A purge would look like rapid disassembly, timed to the opponent's closest approach, and it would paint the inner solar system with fragments whose speeds and dispersion patterns point back to a single event rather than to gradual thermal fracturing. Every one of these outcomes would stamp the tail and coma with signatures that refuse to match space weather timing. Solar wind changes, trigger tail kinks in all comets. A conflict scenario must show changes that ignore those triggers. These ideas also carry built-in falsifiers that protect us from clever excuses. For the relay, if paired anomalies vanish when we correct for angle and distance, and if no narrowband tone appears in deep searches, the story folds. For the harvester, if jet geometry twists exactly as rotation demands, and thermal power lines up with sunlight within ordinary error, there is no energy budget left for collection. For the conflict play, if disconnections happen only when solar wind maps say they should, and if no converging trajectories or fixed separations show up, then the battlefield is just plasma doing what plasma does. There are practical campaigns to run while the glare has us waiting. Stack long, deep images to hunt for, faint co-movers around each visitor. Natural fragments drift outward along the tail and fade. Escorts would keep tight distances that persist. Cross-index tail kinks and brightenings with solar wind data from multiple spacecraft. If every change lines up with a coronal hole or magnetic sector boundary, space weather gets the credit. Build an angle-corrected brightness index for both visitors and run the cross-correlation with a rolling lag. A sustained asymmetric peak would be the first hint of coordination worth chasing. Repeat the most sensitive radio searches during the same hours, from different longitudes to rule out local interference. Publish nulls quickly. The fastest way to keep imagination useful is to feed it honest misses. There is a quiet virtue in saying what would convince you before the data arrives. It keeps the goalposts planted. For a relay, I would need to see paired activity with stable lag after removing, geometry, plus at least one credible narrowband detection that repeats. For harvesters, I would need a persistent thermal excess and a jet geometry that holds still while the nucleus turns. For conflict, I would need converging tracks to a constant standoff distance or a timed breakup that ignores solar wind triggers. Without those, the elegant stories stay elegant, and the comets stay comets. And there is a second virtue in letting these tests run, even when you expect them to fail. Negative results become baselines that make the next strange thing easier to judge. If some future visitor twitches in a way this pair did not, we will notice sooner because we rehearsed our skepticism here. That is how thought experiments earn their keep. They drive us to collect exactly the kind of clean, timed, multi-angle data that makes ordinary physics sing and extraordinary claims stand or fall. When the curtain lifts after the glare, the checks will be waiting. Either the stories get quieter, they get stronger. Either way, we walk out with a better map of what the sky can do. Every comet is a windsock for a star. Dust shows you where sunlight pushes. Ionized gas shows you where the solar wind flows. Watch long enough, and you begin to see the sun's moods traced onto a moving canvas. That is the quiet superpower of SWAN R2 and 3 Eye Atlas. They are not only visitors, they are instruments that let us read the space weather around them in real time. Start with the two tails that most photos reveal. The dust tail is the painter's brushstroke, wide and soft, curving gently because larger grains drift slower and remember yesterday's push. The ion tail is the metronome, thin and straight, pointing almost exactly away from the sun because the solar wind grabs charged molecules and drags them downfield. If you see a graceful bend, you are looking at dust. If you see a razor line, you are reading plasma. Now, add the sun's rhythms. Our star spins roughly every 27 days. As it turns, long-lived features ride across its face. Coronal holes blow steady, high-speed wind. Active regions pop and fizz with magnetic complexity. From time to time, a coronal mass ejection blows a bubble of plasma into space. When that bubble reaches a comet, the ion tail can kink or break and then rebuild. This is a disconnection event, one of the most delicate pieces of drama the sky offers to backyard eyes. Geometry decides how clear the drama looks. Phase angle changes how much of the tail we see lit toward us. Elongation determines whether the comet is viewable at all. Even with those constraints, space weather leaves signatures that cut through the noise. A coronal hole stream arrives and the ion tail stiffens and brightens. A mass ejection hits and the tail snaps, then grows a fresh, straight segment aligned with the new magnetic flow. A day later, the dust tail still looks like a slow curtain because dust does not care about magnetic fields. Two tails, two truths at once. This is not just pretty, it is diagnostic. Ion tail position gives a direct handle on the magnetic field direction carried by the solar wind at the comet's location. Brightness changes in the ion tail reveal gas production rate and how quickly the wind strips ions away. The spacing of kinks and disconnections can be compared with spacecraft that monitor the sun closer to home. If a snap matches the arrival of a sector boundary crossing in those records, the case for space weather control strengthens. If a snap ignores all obvious drivers, the puzzle grows teeth. 3-Eye Atlas gives us a chance to read these patterns from two balconies at once. Earth may lose the view in glare, but Mars orbiters sit at a different angle. When a disconnection rolls through, the timing difference between what Mars sees and what Earth later sees becomes a clock for the shock's travel time across millions of kilometers. Even a simple sequence of faint frames can measure that lag, well enough to test solar wind models. There is a subtlety worth holding onto. Not every change is a storm. Comets rotate, and jets switch on and off as local dawn and dusk march around the surface. That creates small waves in both tails that repeat with the spin. Space weather superimposes larger moves that do not care about rotation. Separate the two and you can tell whether a flare in the ion tail came from a vent, waking up, or from the wind stiffening down the line. The trick is cadence. You need enough frames across hours and days to see what repeats and what does not. SWAN R2 is a gift for this because it is bright and lives in the evening sky. If you photograph it across several nights and lay the images side by side, you will often see the dust tail changing slowly, while the ion tail twitches. On some nights, a faint diagonal crease appears across the narrow tail. That crease is a magnetic fold sweeping through space and reorganizing the ions. It is the cosmic version of watching a gust of wind ruffle a flag while the flagpole stands still. Forecasting helps solar physicists map coronal holes and active regions as they rotate into view. They model when high-speed streams will wash over planets and comets alike. If a fast stream is due and the ion tail responds on schedule, nature gets the credit. If nothing in the forecast fits and the tail still throws a tantrum, we go back to the ledger and check for outbursts, viewing angle changes, or rare geometry. Only after those checks fail do we allow the word anomaly anywhere near the page. Spectra. Add one more layer. Ion tails glow in specific lines from molecules like carbon monoxide ions and other fragments produced when sunlight breaks apart parent gases. When a storm hits, the line strengths can surge or fade as the flow changes, giving a chemical fingerprint to the same event your camera recorded as a kink. Match those spectral swings to images, and you have both the music and the dance for the same piece of weather. The practical payoff lands after the blackout, when the visitors return to friendly angles. One of the first questions will be whether their tails and Comet tell a normal weather story. Did disconnections match known solar wind features? Did ion tails point where models said they should? Did dust tails curve with the steady push of sunlight, and not with anything more exotic? If yes, the ledger fills with ordinary physics that still feels extraordinary to watch. If no, we circle the mismatches and ask for repeat performances under better angles. You can help write that ledger, a short run of images taken at the same time each evening, even with modest equipment, captures tail direction and gross structure. A quick note about sky conditions and the number of minutes after sunset you began helps fix the geometry. Shared across observers, those notes become a map of how the sun's breath raked across two comets during one remarkable month. So when the headlines talk about mysteries, remember the invisible hands. The sun is always in the story. It pushes, it pulls, it snaps, it smooths. Our visitors simply make those forces visible, thin and blue, and briefly bright against the dark. Read the tales and you are reading the wind. Before October gave us a double act. The word interstellar meant two very different stories. One was the strange shard that raced through in 2017 and left us arguing. The other was a classic comet from 2019 that behaved so cleanly it felt like a control experiment. Put them beside 3i Atlas, and you start to see a pattern that is messy in ways that science likes. It is the kind of messy that pushes better questions onto the table. Begin with 1i Oumuamua, the first object we ever caught that did not belong to our sun. It arrived faint, fast, and without a visible coma. Light curves hinted at an elongated or flattened body, tumbling end over end. A geometry that made artists draw either a cigar or a pancake. The surprise was a tiny but measurable non-gravitational acceleration as it receded, the sort of extra push you expect from gas jets, even though telescopes did not see the usual dust and vapor. That mismatch spawned years of debate. Exotic explanations bloomed because the simplest picture had missing pieces. Maybe it outgassed in a way that produced little dust. Maybe it shed molecules we did not track well at the time. Maybe it was thin and odd, and sunlight itself did more of the work than we realized. The lesson was not that mystery equals machine. It was that sparse data taken late in a brief window can leave room for arguments to grow. 2i Borisov, discovered in 2019, reset the tone. It was unmistakably cometary from the start, with a coma, a tail, and gas ratios that looked unusual yet comfortably natural. It shed carbon monoxide generously, a sign it formed far from the warmth of its parent star. Water lines grew stronger as it dropped inward, exactly as classroom physics says they should. No odd acceleration, no crisp radio tone, no thermal budget. You could not close with sunlight. It was the opposite of a cliffhanger. It was a reminder that interstellar does not mean inexplicable. It can mean ordinary physics in a different accent. Now place 3i Atlas between those two bookends. It glows green at times because carbon molecules and cyanogen light up under ultraviolet sunlight. It carries nickel lines that show clearly while iron lines are faint or absent during specific windows. Its early activity leaned on carbon dioxide while water stayed quiet, which is what cold visitors often do. Far from the sun, it is small, likely patchy, and on a retrograde hyperbola that will never loop back. It shows no steady shove that ignores day and night. it sings no narrowband radio. If you feel the echo of Borisov in that list, you are not wrong. If you also feel the itch of Oumuamua in the odd nickel story and the timing that pushes observations into glare, you are not wrong either. The better comparison is not vibes, it is logistics. Oumuamua taught us the cost of late discovery and short baselines. By the time we realized what it was, the best instruments had little time to plan. Borisov taught us the value of early, routine spectroscopy and high-cadence imaging. We got chemistry and timing early enough to watch it change. With 3i Atlas, we did both things better. Surveys flagged it when it was still far out. Space and ground telescopes banked spectra before the blackout. Mars gives us a side balcony during the weeks when Earth stares into sunlight. Even if some details stay odd, we will come out of the glare with before and after measurements that let the ledger balance or refuse to. The chemistry fits the broader lesson too. Oumuamua's lack of obvious gas pushed arguments toward shape and surface physics. Borisov's rich gases pushed arguments toward formation environment. 3i Atlas splits the difference. Carbon dioxide drove early, which points to a cold birthplace. The green tint and cyanogen suggest organic chemistry ready to wake. The nickel without easy iron invites microphysics. How grains weather, how fragile compounds break, how ionization favors some lines over others inside Apache coma. None of that requires invention. All of it requires patience. Media history matters here. Oumuamua's acceleration headlines jumped faster than the calibration did, and the conversation never quite recovered. Borisov suffered the opposite fate. Spectacular for scientists, quiet for most of the public. 3i Atlas arrives in a more mature environment. We can say what would convince us of engineering before we measure it. We can list the natural expectations across distance. Carbon dioxide first, water later. Rotation tide wiggles in the light curve. Ion tail moves that match space weather maps. If those show up on schedule, the ordinary wins with receipts attached. The detection pipeline has grown sharper in the meantime. More sky, deeper reach, faster reporting. That matters for SWAN R2 as well, because it shows how selection effects shape our calendars. A long-period comet hid in glare, then stepped into twilight. As if on cue, Oumuamua would likely have been less mysterious if surveys this capable had existed a decade earlier. Borisov made the most of their rise. 3i Atlas and SWAN R2 mark the next turn of that ratchet. There is one last shared thread. All three interstellar cases so far have reminded us that outliers are teachers. The odd rotation of Oumuamua forced better thinking about how brittle surfaces behave. The cold chemistry of Borisov recalibrated where and how comets can form around other stars. The layered activity and metallic quirks of 3i Atlas are already nudging us to improve models of grain evolution, excitation, and the ways early sunlight sorts molecules inside Apache coma. Even if nothing exotic hides inside the glare, the upgrades to our playbook will survive into the next decade and the next visitor. So do the comparison with clear eyes. 1i Oumuamua was a whisper and a puzzle. 2i Borisov was a loud yes to natural comet physics with a pleasing twist. 3i Atlas is an in-between that leans toward Borisov while still leaving a few doors ajar. The difference this time is not only what the comet is, it is how we are watching. We have the before, we will have the after. The gap in the middle will not be a void, it will be a test. The curtain falls not with drama but with daylight. Both visitors slide into glare. The feeds get noisy. And the most interesting chemistry happens when our best eyes can barely look. That is the silence people mistake for waiting. It is not waiting. It is a breath before the test. Because the moment, 3i Atlas and SWAN R, two-step, back into friendlier angles, we will not ask how they look, we will ask how they changed. The ledger we built before the blackout tells us exactly where to look for the answers. First comes light itself. We measured clean brightness curves, while the angles were kind. We will measure them again and subtract. Natural physics predicts a set of simple outcomes. As distance from the sun grows, production falls with a known slope unless fresh vents opened. Rotational wiggles should come back with the same beat, unless outgassing torques sped the day up or slowed it down. If the rhythm returns with a small phase shift, the spin rate changed a little. If the rhythm vanishes, a major outburst rebuilt the surface and reset the clock. Next comes color. which is chemistry in disguise. Before the blackout, 3i Atlas leaned green because carbon molecules and cyanogen were doing the loudest singing. After the blackout, water should have taken a larger share as deeper ice warmed. That means hydrogen maps from solar instruments should glow stronger and the visual tint should soften. If spectra still show a coma, ruled by carbon dioxide long after perihelion, the thermal story is wrong or the surface sealed itself under a fresh mantle. Either way, the comparison matters more than any single frame. Metals get their own checklist. Nickel lines showed up during specific windows while iron was quiet. If the imbalance was about temperature and excitation, iron should now step forward as heating and geometry change. We do not need dramatic swings, only a steady rise in the iron lines, while nickel holds a calmer course. If iron remains stubbornly absent across many dates and instruments, the microphysics case gets louder and the outlier label earns a second pass. Oddity without persistence is gossip. Oddity that survives new angles is evidence. Tails turn wind into geometry. We already logged the ion tail directions and kinks and lined them up with solar wind forecasts. After the blackout, we will do the same and look for the same lockstep. Repeated disconnections that match known magnetic sector crossings would confirm that plasma, not purpose, writes, the sharpest moves, a dust tail that curves with the gentle push of sunlight and remembers, yesterday's shove, says the big grains flowed the way they should. If any tail keeps a fixed shape that ignores rotation and wind, we will circle it in red and ask why. Motion is a quiet truth teller. Fit the trajectory again with all the fresh positions. The residuals should breathe with rotation and sunlight, not hold a constant push in one direction. A small change in the spin rate should show up as a small change in the non-gravitational acceleration pattern, not as a steady thrust that ignores day and night. If the fit refuses to settle without a constant extra shove, that would be new. We are not betting on it. We are watching for it with the same rules we would use for any visitor. Fragments are the most obvious surprises. Close solar encounters sometimes crack brittle surfaces. When a comet breaks, it leaves a family. We will stack deep frames and hunt for faint companions that share the motion. Natural fragments drift outward along predictable lines, spread with time, and fade. Pieces that hold a constant separation would be a different story. A clean family spread would also help explain any sudden changes in brightness or chemistry by replacing mystery with debris. Mars gives us a cross-check. If any orbiter captured even modest coma profiles or tail angles during the Earth glare window, we can stitch those into the sequence. A faint elongation seen from Mars that continued later from Earth turns into a timeline rather than a guess. A spectral hint from Mars that water woke earlier than expected becomes a note to hit again. With ground instruments, from two balconies, the same play becomes easier to follow. We will also rerun the simplest citizen tests because they scale better than people think. How many minutes after sunset before SWAN R2 becomes obvious again? Does that number fall as expected? Or does it hang stubbornly high, as if dust production stalled? Does 3i Atlas pick up its green breath at the same brightness where it left off? Or does the color curve lag? Thousands of small, consistent notes can spot a trend faster than a few perfect spectra. The prediction game keeps us honest. Here is the scorecard that ordinary physics expects to win. For 3i Atlas, a gradual shift from carbon-driven to water-visible signatures, a rotation beat that either returns or moves by a small and explainable amount, iron lines that strengthen relative to nickel as temperature and angle change, and tail behavior that matches the solar wind map. For SWAN R2, a tail that thins and lengthens as production falls, occasional kinks when space weather snaps, and a steady slide down the brightness curve set by distance and angle, rather than by any unseen clock. If the sky delivers that set, the story lands clean. The double act was rare and beautiful, and entirely natural, and our instruments read it correctly before and after the gap. If the sky delivers something else, the second act will not be chaos. It will be a direction. Persistent metallic imbalance with no thermal excuse. Fixed geometry and a jet that ignores rotation. A constant non-gravitational push that does not care about sunlight. A companion that holds station. Any one of those would not close the case. It would tell us which test to double down on next. Silence is not suspense for its own sake. It is the space where predictions harden into checks. When the glare fades, the ledger opens. Not how do they look, but how do they compare to what they promised before the curtain fell? That is the moment science lives for. The applause can wait. Numbers first. When the glare fades, the work does not start. It resumes. Every frame we take was already promised by a plan written before the sky went white. The plan is simple to say and hard to do. Turn light into numbers, numbers into patterns, and patterns into claims that survive strangers checking them. The pipeline that carries that truth is not glamorous. It is the reason stories either stand or fall. First, photons meet glass, telescopes gather light, and feed it to detectors that turn it into counts. Those counts carry scars. The sensor has warm pixels. The optics scatter light. The night breathes, and the air ripples. Teams subtract those scars. With calibration frames that measure the detector's own glow and the way a flat field should look if the system were perfect. Only after that hygiene do we allow ourselves to call the remaining signal the sky. Spectra follow the same rules with more moving parts. A slit lets a thin ribbon of light through. A grating spreads that ribbon into a barcode where distance along the detector is color. Lamps with known lines set the ruler. Standard stars set the brightness scale. Then we subtract the sky again because the air glows and the telescope breathes. When a line survives all of that, it has earned the right to be believed. When it fades with better subtraction, it goes back where it belongs, on the list of ghosts. Images go to astrometry, which is the art of putting a precise place and time on the sky into a clean coordinate. Software matches star patterns to catalogs and corrects tiny distortions. Out of that comes a position for the comet with an uncertainty bar that is honest. A single position is a postcard. A string becomes a path. Fit that path, and the residuals tell you whether sunlight and venting explain every nudge or whether something else is shoving. Honest uncertainties are the difference between a plot twist and a false alarm. Photometry turns images into light curves. We pick an aperture, sum the counts inside, subtract the background, and convert the result into a brightness scale that other people can check. Then we repeat with a slightly different aperture to make sure our choice was not flattering only to our own. Theory: a jagged curve can mean rotation, vents, or weather in space. It can also mean clouds and focus. Redo the reduction blind with a second pipeline and see if the wiggles stay. If they do, call them real. If they do not, call them lessons. The same humility powers cross-checks between instruments. A ground spectrograph says nickel is loud and iron is quiet. Fine. Now ask a different telescope to take the same band with a different detector. Ask an infrared instrument to look for iron in a line that lives beyond the visible. Ask a space telescope to sniff the same lines without air in the way. Corroboration is not redundancy. It is insurance against being fooled by your own favorite tool. Models sit in the middle of all this, like translators. A coma model takes a guess at how fast gas expands, how big dust grains are, and how sunlight scatters off them. It then predicts how bright the head should be and how fast that brightness should drop with distance from the center. If the model needs wild parameters to match a mundane image, be suspicious. If a simple model catches the main shape and the tail angle while leaving small structured errors, the physics is probably right, and the details are an invitation to refine rather than to invent. Statistics are the quiet spine. Before the blackout, we wrote down what would count as convincing. That is a prior in plain language. After the blackout, we calculate how much the new data should move that prior. That is a posterior without the math on screen. Confidence grows when independent teams get the same answer. Confidence shrinks when the answer depends on one night, one filter, or one reduction recipe. A claim that survives strangers doing it differently is a claim worth repeating aloud. Open data makes this faster. Many observatories now post reduced frames and spectra on public servers within days. Amateur networks share raw stacks and processing notes, when someone elsewhere can download your files, run their own code, and get your plot. The conversation moves from opinion to verification. Null results belong in the same stream. If a careful search for a narrow radio tone found nothing during the best geometry, that absence is a datum with real weight. Publishing it keeps the field honest and saves others from chasing the same mirage. The pipeline also includes something that is not a tool. It is time. Peer review and community scrutiny slow the pace on purpose. That delay is not a gate against excitement, it is a filter against error. The strongest claims from bright months, they often arrive a little late because the best authors let other hands try to break the result before they go to print. In a season as loud as this one, patience is courage. None of this precludes wonder, it protects it. When the light returns, we will line up the before and after, and let calibration and statistics fold the difference into meaning. If water grew as expected, if iron lines strengthened relative to nickel, if tails obeyed the wind maps, the ordinary winds with beautiful precision, if something resists those fits, the pipeline will not hide it, it will expose it and ask for more. Either way, the story we tell you will be the same one the numbers told us first. So when you hear a headline, imagine the miles it traveled. From photon to pixel, from pixel to spectrum, from spectrum to plot, from plot to paper, from paper to someone across the world, starting from zero and landing in the same place. The path is tedious in the best way. It is also the reason we can look into a camera and say with a straight face what is likely, what is possible, and what is noise. The sky gives us gifts. The pipeline earns them. Every investigation that keeps you up at night narrows toward a fork. One road is tidy, the other is thorny. When 3i, Atlas and Swan are two-step back out of glare, the numbers will push us onto one of those paths. Either the ordinary wins with elegance, or the case refuses to close and asks for more light, more angles, more courage. Both endings matter, both change what we do next. Start with a clean landing. Natural winds does not mean boring. It means the ledger balances without contortions. The rotation beat returns within a breath of where we left it, maybe shifted by a small torque from outgassing. Color tilts from carbon-driven greens toward water's quieter signatures. As deeper ice takes over, iron lines grow toward parity, while nickel relaxes into the background, ion tails point where. Space weather maps say they should, and snap when a coronal mass ejection rolls through. Brightness curves slide down the slope set by distance and angle. Move the ruler from before to after, and the ticks line up. That ending is a gift. It lets to us cash in what we learned about early activity, layered ices, and how fragile grains evolve under sunlight. It also clears the speculation fog and sharpens attention on the real physics that makes comets glow. The neat ending carries deeper winnings. It tells us that surveys now catch these visitors early enough to build baselines that survive a blackout. It proves that a side balcony like Mars can stitch a story while Earth blinks. It shows that citizen, logs, backyard images, and professional spectra together can read a month of space weather to off two moving windsocks. It hands teachers a perfect arc to bring into classrooms: prediction, obscuration, return, comparison, conclusion. It hands planners a stronger argument for the next generation of sky cameras and infrared surveyors that will find the next wonders earlier and fainter. If the tidy road is real, the headline will not be less thrilling, it will be more honest. Rare alignment, rich chemistry, no monsters in the closet, wonder without fear. Now, the thorny road, the case gets weird, does not mean lights in the margin and secret machines. It means at least one stubborn mismatch survives fair tests. Perhaps iron stays quiet across many dates, while nickel keeps singing under conditions that should have woken both. Perhaps a jet geometry holds fixed through rotation, longer than messy terrain allows. Perhaps a small extra push refuses to bow to day and night. Perhaps the companion piece keeps the same separation for too long to call it drifting debris. None of those alone proves the extraordinary. Each of them narrows the ordinary and raises the bar for our next measurements. If we earn the thorny ending, we do not reach for the wildest story. We reach for the sharpest plan. That plan starts with cadence, more nights, more instruments, a campaign that makes single-night myths impossible. It continues with Angle's southern and northern teams trading. Coverage Mars assets pointed again. If geometry allows, solar monitors, flagging wind changes in real time so we can sort the weather from the source. It expands into spectrum coverage that fills gaps we left the first time. If visible lines tease us, go infrared. If dust hides, the core, go radio for large grains. If jets look suspicious, push for polarimetry to fingerprint grain sizes and textures. If a constant push appears real, we test it against every natural nudge we know. Outgassing models with many vents, spin state changes that evolve over weeks, solar radiation pressure on dust, masquerading as a force on the nucleus. Only when the residual refuses every weather, and geometry trick, do we allow the words persistent acceleration to stand without apology. If a companion holds station, we play the dullest games first. Is it a background star folded by processing? Is it a ghost from optics? Is it a fragment we caught at the start of a drift? Only after that gauntlet do we chase it with deeper stacks and wider baselines. The thorny road also comes with a public duty. We must say out loud what would change our minds. A repeating clock that ignores rotation and distance. A narrowband radio tone that repeats on demand. A radar echo stronger than ice should. Allow A, thermal excess that sunlight cannot supply. A station-keeping companion that survives new angles. These are big asks on purpose. They keep the goalpost still while the field shifts. If any shows up, the conversation changes from maybe to show me again. If none shows up, we report that too, and explain why good weirds turned out to be camera tricks, weather, or our own eagerness. There is a third path that is easy to miss, the near-tidy. In it, most dials settle where physics predicts and one or two stay odd but small. The nickel-to-iron ratio never quite matches simple heating models, yet it slides in the right direction. The rotation beat returns, but with a new gloss that hints at a large outburst we did not catch. The ion tail follows the wind, but the dust tail carries a subtle kink we cannot reconcile. This ending is not a cliffhanger, it is a syllabus. It tells lab chemists to play with nickel-bearing ices in vacuum. It tells dynamicists to refine how mantles crack and reseal. It tells plasma modelers to tweak how grains and ions share momentum near thin Comet. The payoff is slower and deeper. The result is better models long before the next visitor arrives. Here is the quiet comfort across all three endings. We do not lose. If the ordinary wins, we win clarity and a sharpened playbook. If a small set of stubborn clues survives, we win targets for the next round of discipline tests. If something truly out of family appears, we win the chance to be careful with a discovery that could change how we think about our address in the galaxy. The only way to lose is to rush past the fork and pick a road because it feels good. So when the first post-glare spectra drop and the first images with long tails land, hold your breath for exactly one beat. Then ask the only question that matters: which road did the numbers choose? If it is tidy, celebrate the precision. If it is thorny, celebrate the hunt. Either way, the sky did not owe us a choice this. Clean, it gave us 2 visitors, 1 month, and a fork that is more than enough to keep curiosity honest. No matter which road the numbers choose, this month leaves us with a to-do list written in starlight. If the ordinary wins, we double down on what worked and scale it. If the case gets thorny, we tighten the net and raise our standards. Either way, the next visitors will meet a different species than the one that greeted Oumuamua. We will be ready earlier, with cleaner baselines, faster coordination, and millions more eyes pointed in the same direction. First, earlier discovery. Surveys are our front line. The more sky we cover every clear night, the sooner faint wanderers cross the threshold from invisible to trackable. That means bigger cameras, wider fields, faster pipelines, and dumb simple rules that do not miss a single moving pixel. The lesson from 3i Atlas is ruthless. A few extra weeks of lead time turned into spectra before glare. Next time we push for months, that is not fantasy. It is engineering plus budget matched to a clear goal. Second, automatic playbooks. This season proved that the best science happens when checklists launch the moment an alert fires. Image here, spectrum there, radio listen during this window, infrared during that one, then repeat at a fixed cadence until the object sinks into the sun. The new playbook should be public, boring, and widely adopted so that amateurs and professionals can run the same beats and stack compatible data. One comet, one score, thousands of instruments marching to it. Third, side balconies on purpose. Mars earned its seat as an accidental witness. We can do better. Orbiters around other worlds can carry small observation modes that point outward for an hour when geometry is golden. Even tiny CubeSats riding along to the Moon or to Venus can hold simple cameras that look away from their primary targets on pre-planned days. The cost is low. The payoff is an extra angle during the exact weeks. When Earth goes blind, multiply that across a few platforms, and the blackout stops being a gap and becomes a triangulation window. Fourth, the classroom ladder. Students do not need permission to measure the sky. They need a ladder they can climb. The ladder looks like this. Night 1, learn to log when the head becomes obvious. Night 2, measure tail angle against bright stars with a phone held to binoculars. Night 3, upload a stack and a short note about conditions to a shared map. In a week, a class can watch a tail react to a solar wind stream without ever touching a professional instrument. Those logs matter. They fill time gaps and turn isolated frames into a movie. Fifth, radio and radar time on call. The cleanest falsifiers for wild claims are tones and echoes. We do not hear them often, and that silence speaks. But the ability to listen on short notice is essential. That means arranging flexible, observing windows at a few radio dishes and keeping scripts ready to run. When a visitor hits a sweet geometry, we do not scramble. We press go. If nothing sings and nothing reflects beyond fluffy dust and ice, that null becomes a strong comma in the story rather than a footnote. Sixth, chemistry in the lab. This month highlighted how much we still do not know about fragile compounds under sunlight and vacuum. Let us bring pieces of that coma to Earth. Not literally, but in chambers that mix ices, organics, and trace metals, and then hammer them with ultraviolet light while we watch the spectrum bloom. If nickel can glow without iron in a specific pathway, find it. If cyanogen and diatomic carbon carve that green halo under a narrow set of conditions, measure them. Every lab curve we bank is an ambiguity. We retire before the next debate starts. Seventh, transparency as culture. The fastest way to separate signal from noise is to share more and earlier. Calibrated frames, reduction code, even the failed attempts that taught us what not to try. When anyone, anywhere, can rerun your pipeline and land on your plot, the conversation jumps past opinion and into verification. That spirit belongs as much to backyard forums as to journals. The sky is big enough for all of us, and the best ideas survive contact with strangers. Eighth, citizen observatories in the dark band of the world. There are long arcs of Earth where clear skies and low light pollution are normal. Small, the well-placed stations in those arcs can watch twilight angles that big facilities miss. A handful of robotic mounts with fast lenses, a fair internet link, and volunteers trained to babysit the weather, and the focus can add nights that professional schedules cannot. In a season like this, those nights are not marginal, they are gold. Finally, dare to ask bigger. If the case ever stays weird after fair tests, the answer will not come from a clever tweet. It will come from hardware. A quick flyby probe that can intercept a hyperbolic visitor with a camera, a spectrometer, and a dust sampler. A coronagraph optimized for the inner sky that lets us keep watching when glare would normally close the curtain. A small fleet approach rather than a hero craft, because redundancy is how you catch a surprise in the act. These are not dreams. They are line items with price tags that match their return. Here is the part where you matter most. The next time a faint wedge lifts out of the twilight, go look, note the time, share a frame, encourage a friend. If you run a lab, give a team a chamber and a week with ice and light. If you run a telescope, leave room in the queue for a sudden comet night. If you write software, polish a tool that makes reduction easier for someone who has never tried. If you teach, put a comet on the board and give your class a reason to step outside. We do not control what the sky throws at us. We control how ready we are when it does. This month taught us that readiness multiplies wonder. It also taught us that careful rules and open hands to make the loudest months the most honest. The next visitor has already started home from some cold nest around a distant star. When it finally crosses our threshold, let it find a planet that has learned from October. Let it find a crowd that can be thrilled and precise at the same time. You and I have walked a long arc together. From the first whisper that two strangers were racing the sun, through chemistry and wind and the hard math that keeps stories honest, all the way to the fork where Tidy and Thorny waited. Whatever the numbers finally chose, the gift of this month is already clear. October taught us how to watch with both eyes open. One eye for wonder, one eye for proof. Maybe the ledger closed clean. If so, take a breath, and enjoy the rarest version of satisfaction our species gets. We asked if the ordinary is enough. It was two travelers crossed our sky and behaved like ice and dust under a hot star. The romance does not fade when the physics fits. It sharpens. Those green breaths, those nickel lines, those patient tales were not hints of machine. They were signatures of ancient chemistry waking on cue. The play was written at a nursery we will never see, and we still learn to read it by lamplight from one small world. Or maybe the ledger left an asterisk. If a few stubborn clues survived real tests. That is not license to sprint into fantasy. It is permission to keep asking better questions. A mismatch that repeats is not a rumor. It is a direction. Aim telescopes, aim lab lamps, aim time and stubbornness at the small place where the map still says here, be dragons. Good science is a detective that loves dead ends because they narrow the street where the real door waits. Either way, the deeper truth here is not the fate of one visitor or two. It is what we built in the watching. A planet-sized team that could move from gasp to measurement in days. A ladder students could climb. A culture that learned to say what would change our minds before the data arrived. That is not only a workflow, it is a promise. The next wanderer will find us sharper, calmer, faster with the checklist, and slower with the hype. That is progress you can feel. So where does the story end? Not with a verdict, with a habit. When the sky throws a paradox at you, start a ledger. Write what nature should do if this is only ice and heat. Write the tells that would make you believe otherwise. Collect the frames, subtract the ghosts, compare before and after without mercy, then say out loud what survived the subtraction. If the answer is ordinary, you have won a clean lesson. If the answer is odd, you have won a clean question. Both are the engine of every real advance we have ever made. There is one more quiet reward I hope you carry out of this month. Curiosity is not a mood. It is a choice you make over and over when a headline tries to drive, when a rumor feels good, when a plot twist begs you to share first and check later. Curiosity says look again. It says ask the boring question about angle before the thrilling one, about intent. It says the sun has invisible hands, and sometimes that is the whole story. It also says, leave a little room for surprise, because the universe has a sense of timing we barely understand. If you stood under the evening sky and watched SWAN R2 lift its pale fan, you already know why this work matters. If you traced the green breath of 3-eye Atlas in a small telescope, you carried home a souvenir that no screen can fake. This is how a species learns to care about the world beyond its weather and headlines. One eye at a time, one note at a time, one small shared gasp that becomes a map. Here is my ask as our credits roll. If this investigation lit a spark, keep it fed. Subscribe so you are in the room when the next alert fires. Drop a comment with your own notes from the field so other viewers can compare and learn. Share this film with the person in your life who loves a clean explanation as much as a wild theory. The more of us who practice tidy curiosity, the better our chances when a truly weird thing finally strolls across the stage. Comet, fortress, or reply. The month taught us how to test the words without breaking the wonder. That is enough for tonight. The sky will write a new chapter soon. When it does, meet me outside. Bring a jacket. Bring a friend. Bring the version of yourself that can be thrilled and precise at the same time. We will point up, start a ledger, and see what the light says.